Okay, so we've talked about kinematics, motion in one dimension, but so far, pretty much everything we've talked about is most easily understood in the x-axis. Get in your car and you step on the accelerator and you accelerate at a constant acceleration for some amount of time, something like that. Um, that's an important point here. The equations of kinematics work for the case where there's constant acceleration. That means that the acceleration could be zero, and it's always zero, in which case this equation is your final velocity equals your initial velocity times plus zero times time. Well, that just disappears if acceleration is zero, so your final velocity equals your initial velocity. It's kind of obvious. Um, this one doesn't have acceleration in it. This one, final velocity squared equals initial velocity squared if all this is zero. And then down here, distance equals velocity times time. That's an equation that we already knew when we started the class. Plus 1/2 at squared. Well, if acceleration is zero, this whole term goes away and just distance equals velocity times time. So that's one instance if the if the acceleration is zero. Now, if the acceleration is not zero, if the acceleration has some value, then we have that value to plug in. Well, there's a case in the y-axis where we would have a constant acceleration. We call that the acceleration due to gravity. And so I'm just skipping ahead to get to this point. So in the absence of air resistance, and that's there is air resistance. There always is some air resistance. If you drop I don't know, a rock, why are you dropping a rock in the water? I don't know. But you're in the water and you drop a rock. It floats kind of down to the bottom of the water. You know, try this sometime if you're at a lake. Something that sinks in the water, you can watch it sink down, but it doesn't fall the same way that it would fall in the air. Because water is this thick fluid that it has to push its way through. Well, in air is a fluid, and in the absence of air, things would fall without air resistance. So, in the absence of air resistance, it is found that all bodies at the same location above the Earth fall vertically with the same acceleration. If the distance of the fall is small compared to the radius of the Earth, which most reasonable distances would be, then the acceleration remains essentially constant throughout the descent. This idealized motion is called free fall, and the acceleration of a freely falling body is called the acceleration due to gravity. So, what we'll say is for a reasonably small fall here near the surface of the Earth, the acceleration due to gravity, the a that we would plug into one of our equations, is equal to lowercase g, and that's 9.8 meters per second squared. Now, 9.8 meters per second isn't a very small velocity, so a fall of just a fall that has a duration of 1 second gives you a pretty good velocity. So that's what happens when you drop things, or if you fall, if you jump off of a wall or something, you will accelerate at this 9.8 meters per second squared. Now it turns out that say you jump out of an airplane wearing a parachute, you will be in free fall motion. You will accelerate at the acceleration due to gravity until such a point that air resistance, and there will be some air resistance, equals the force that is pulling you down. The force that's pulling you down is your weight, mass times gravity. We'll talk about that in some upcoming chapters. But so there's a force pulling you down, and then air resistance would be pushing you back up. And when those two things are equal, you stop accelerating and you have this final velocity. It's called a terminal velocity. And if you were to go skydiving and you jump out of an airplane, your terminal velocity is around 100 miles per hour. So you will accelerate for a little while after you jump out of the airplane, and then air resistance with your body and your fall would equal out. So, you don't keep accelerating. You won't smash into the ground at the speed of sound, 330, 340 meters per second. You would smash into the ground. It's around 100 miles per hour, whatever that is in meters per second, which, isn't any great comfort, because if you hit the ground at 100 miles per hour, you're not likely to survive that fall, but that's as fast as you're traveling. All right, so I don't know if you've seen this at the Museum of Science. They have an example where they lift up a feather and a rock, and then you can either evacuate the tube, pump out all the air, or leave the air in there, and you discover that in the absence of air resistance, they fall at the same rate. So mass is not a factor in the acceleration due to gravity. What will matter is the air resistance. So if you have a sheet of paper versus a textbook and you drop them both to the floor, the textbook slams down to the floor and the sheet of paper kind of slowly flutters down. But if you crumple up the sheet of paper and drop the textbook and the sheet of paper at the same time, they will hit the floor at the same time, even though they have a decidedly different mass. So, a falling stone. A stone is dropped from the top of a tall building. After 3 seconds of free fall, what is the displacement of the stone? So the trick here, we have an initial velocity. They drew a picture for us. That was nice. We have an initial velocity. We have a time of 3 seconds. We need to know 3 of our variables. So we know initial velocity, we know time. The other variable that we would know then, presumably this is taking place on Earth, near the surface of the Earth. So we also know the acceleration due to gravity. Acceleration A equals G, which equals 9.8 meters per second squared. And if we're going to orient ourselves here, the top of the building is in the positive y-axis, and the ground level is moving toward the negative, down towards 0. So the acceleration due to gravity is also in the negative. It is pulling down toward the surface of the Earth. So if we list our 5 kinematic variables, the ones that we know are the acceleration is negative 9.8 meters per second squared. The initial velocity was 0. The time was 3 seconds. We don't know the final velocity, but that's not our concern with this problem. We're looking for the displacement, y. And that too will be a negative number, right? Because the final displacement will be down here somewhere, minus the top. So some small number minus a big number will give us a negative number. So we have the 5 variables. We look at our equations of kinematics for the one that doesn't have final velocity in it, and it turns out that it's this one. We're just plugging in y instead of x because that's what we're talking about. So v naught t, the initial velocity times time. The initial velocity was 0 times anything is 0, plus 1/2 times negative 9.8 meters per second squared, times the time they gave us of 3 seconds squared. So 3 squared is 9, times negative 9.8 times 1/2 gives us negative 44.1 meters. It's a negative number. The displacement, the change in position, is negative 44 meters. It fell down 44.1 meters. That's what that means. Another kind of tricky question, I guess. The referee tosses the coin with an initial speed of 5 meters per second. In the absence of air resistance, how high does the coin go above the point of release? So in this picture, they give us the trick here. The initial velocity is positive 5 meters per second. The final velocity at its maximum height is going to be 0. You can practice this at home. Toss anything up in the air. It goes up until it stops going up. When it stops going up, it will turn around and come back down. At its maximum height, its velocity is instantaneously 0. So this coin has a positive velocity, positive velocity, positive velocity. It's getting slower and slower and slower until it stops, and then it has a negative velocity, really small, bigger, 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 big negative velocity until it reaches the hand again or hits the ground or whatever. So here we know the final velocity, the initial velocity, and again we know the acceleration due to gravity. Didn't know the time. Wanted to find the y-axis displacement, the maximum height. So it's the y-axis displacement when the final velocity is 0. That's when it is at its maximum height. So it's this equation, v squared equals v naught squared plus 2ay, or 2gy if you wanted to do it that way. Want to solve for y, so I'm going to subtract v naught squared from both sides of the equation. I'll get v squared minus v naught squared. Then I'm going to divide both sides of the equation by 2a. So I get this y equals v squared minus v naught squared divided by 2a. So 0 squared is 0, minus 5 squared. So I get negative 25 in the numerator, divided by, and then you got to be careful with your calculator here, because you might do 25 divided by 2 equals something, times 9.8, and you get the wrong answer. So you have to make sure you do 0 squared minus 5 squared, that's 25, divided by, kind of in parentheses here, 2 times negative 9.8. This is negative 19.6. So negative 25 divided by negative 19.6, and I get a positive number. Negative divided by negative, and I get positive 1.28 meters. So this coin would go up to a height of 1.28 meters above the hand, and then would stop and turn around and come back down. All right. There are 3 parts to the motion of the coin. On the way up, the coin has a vector velocity that is directed upward, has decreasing magnitude. It's getting smaller and smaller until it stops. At the top of the path, the coin momentarily has a 0 velocity, so that's 0. And then on the way down, the coin has a downward pointing velocity with increasing magnitude. It's getting faster and faster on the way down. In the absence of air resistance, does the acceleration on the coin, like the velocity, change from one part to another? No. The acceleration is constant. It's constant acceleration pointing down at negative 9.8 meters per second. That's why it slows down on the way up. That's why it changes direction at the top and starts coming down. And that's why it speeds up on its way down. We have constant velocity. Constant acceleration. Ugh. All right, we can take advantage of symmetry. So if we launch something up off of a cliff and then we drop it off the cliff, the thing that we can know is that with constant acceleration, it will slow down, slow down, slow down till it stops, and then speed up, speed up, speed up, speed up, till it achieves the same velocity on the way down as it had on the way up. So that's true for anything. If you toss a baseball up in the air at a initial velocity of 10 meters per second, when it comes back down to your hand level, it will be traveling at 10 meters per second. So there's a symmetry there. If it's constant acceleration, slowing it down to stop and then speeding it up again, that acceleration will achieve the same velocity on the way down as it had on the way up. Okay, science, we use graphs to describe things. So this is a graph of position versus time. Position on the y-axis, time on the x-axis. And if you did anything with graphs in your academic careers, you know that the slope of a straight line is rise over run. And so what that means in our case here for a position versus time graph is that the slope of the line, rise, so it went up positive 8 meters in our way our y-axis is described here, and run, it marched forward in time 2 seconds. That 8 divided by 2 gives us, since the units for rise is meters and the units for run, the x-axis, is seconds, meters versus seconds, or meters over seconds, is velocity. So the slope of a position versus time graph is the velocity of the object. Now, this can be true if we have a straight line. It can also be the case if things change. So if we're doing a position versus time graph for this cyclist, they're going to have, you can see kind of a steep, a sharp line. So they have a velocity here, positive 400 over 200. So we're able to figure out the velocity here. Up here with a horizontal line, the velocity is 0. The position stays the same with time. And then here we have a less steep sloped line. This is their velocity of the return trip, their negative velocity, which isn't as fast. It's a slower speed, negative velocity. The other thing we can do is if a position versus time graph isn't a straight line, then we can pick a point and say, gee, what was the velocity at time equals 20 seconds? And we can mark out a tangent line, a tangent to the curve. That's where you kind of look at the curve of the line, the line that the slope of that line would keep changing depending on where you are along this line. And so this tangent line gives us the instantaneous velocity at that position. Likewise, if we had a graph of velocity versus time, so velocity is on the y-axis, time is on the x-axis. When we take the slope of that line, the units are meters per second. That's the acceleration. So if we have a straight line for the velocity graph, we're able to interpret that that's a constant acceleration, and we can figure out what that acceleration is. All right, and now I just have some pictures from the textbook that I kept in here. Good job, you have survived Chapter 2. We'll be in good shape soon. All right, let me find this thing to shut it down.